We've all been there, right? You're playing a game in the cloud, getting remote IT support, or maybe helping a family member with their computer from miles away. But have you ever stopped and wondered what's really going on behind the scenes? Well, today, we're going to pull back that curtain and show you the exact blueprint for controlling any computer from anywhere.
It feels like magic, doesn't it? You move your mouse and a cursor on a screen halfway across the world moves at the exact same time. How on earth does a simple click or a key press on your little laptop translate into a real action on a completely different machine?
Well, it's not magic. It's actually a really beautiful logical process. And we're going to break it all down into 4 simple, easy-to-understand steps. We're going to follow a single mouse click from the moment you make it all the way to its destination.
Okay, so step 1. It all starts with you. The very first thing we have to do is capture your physical actions, a mouse click, a keyboard tap, on your own device. For this whole system, we're looking at an app built with Flutter, which is Google's framework for building one app that can run pretty much anywhere, on the web, your phone, or your desktop.
And what's kind of wild here is how many layers your simple input travels through before it even leaves your computer. I mean, it goes from a physical touch on your mouse to the operating system, then gets handed off to the low-level Flutter engine, and then bubbles all the way up through the framework. It's like a message passing up a chain of command, with each layer translating it just a little bit, until our application can finally understand what to do with it.
So how does the app actually, hear these events? Well, Flutter gives us these specialized tools called widgets. If you want to detect clicks and drags, you use a listener. If you need to know when the mouse just enters or leaves an area, you use mouse region. And for every single key you press, there's the raw keyboard listener. Each one is like a little spy dedicated to listening for one specific type of action.
Okay, so we've captured the input. Awesome. But now we hit our first and biggest problem. A click in the middle of a tiny phone screen is totally different from a click in the middle of a giant 4K monitor. How do we create a universal language for location that works everywhere?
The answer, and this is the really clever part, is a concept called normalization. Instead of thinking in specific pixel numbers, we convert them into a universal relative scale that just goes from 0.0 to 1.0. This right here is the secret sauce that makes the whole system possible.
And this just lays it out perfectly. Look at the absolute pixels. The dead center of a 4K monitor is pixel 1920 by 1080. On a phone, it might be 210 by 430. Sending those numbers to another machine would be complete gibberish. But when we normalize them,
they both become 0.5, 0.5. Boom. Halfway across, halfway down. This is our universal coordinate. Now, it doesn't matter what size the screen is on either end, 0.5, 0.5 always means the exact center. It's just an incredibly elegant solution to a really tricky problem. All right, so we've got our universal language. We've translated our click into something that any screen can understand. Now what? Well, we have to package it up and send it across the internet. The instruction gets packed into this super simple, lightweight text format called JSON. The best way to think of it is like a digital postcard. This one here clearly says, hey, this is a move event, and it happened at location 0.52 on the x-axis and 0.31 on the y-axis. It's simple, it's clear, and it's tiny, which means it's fast. And of course, we have a different postcard for every possible action. A move just needs the coordinates. A down, like a click, needs the coordinates and which button was pressed. And a key postcard needs to know exactly which key was hit. Every action gets its own perfectly tailored message. These little postcards are sent using a technology called WebSockets. Now, unlike a regular website connection that opens and closes, a WebSocket keeps a constant open line between the two computers. Think of it like a dedicated private phone line. This is what makes the whole thing feel so instant and responsive, because there's almost no lag.
we are on the home stretch. Our little postcard is traveled across the internet and it's arrived at the remote computer. Now, something on that computer needs to read the postcard and actually do what it says. That's the job of a small program we call an agent, and in this case, it's written in Python.
So, the agent's job is basically to do everything our first app did, but in reverse. It gets that JSON postcard, it reads the instruction, it translates our universal coordinates back into pixels for its specific screen, and then it tells the operating system, hey, perform this action.
Yep, this reverse translation is called denormalization. The agent takes that universal 0.5 coordinate, it looks at its own screen resolution, let's say it's 1920 by 1080, and it does the math. It calculates that the target is pixel 960 by 540.
It translates the universal back into the specific.
And to actually make the mouse move or a key get pressed, the Python agent uses an awesome library called PyAutoGUI. It has these super simple direct commands that basically inject these inputs right into the operating system, faking it out to think a real person is sitting there with a real mouse and keyboard.
Okay, we've seen all 4 steps. Now let's just zoom out for a second and put it all together. Let's recap the entire journey from start to finish.
So this is the whole pipeline. Our Flutter client on the left captures your raw action. It normalizes it into that universal JSON format, our postcard, and zips it across the network. Then the Python agent on the other end receives it, decodes it, denormalizes it back into specific pixels, and injects it right into the remote operating system.
And there you have it. That's the big secret. The end result is a system where your actions on one device are perfectly mirrored on another, and it doesn't matter what kind of screen or device is on either end. That normalization step, our universal translator, is the real hero that makes it all possible.
So now you know the blueprint. And this isn't just for remote desktops. Think bigger. Think about collaborative design tools where multiple people can draw on the same canvas, or remote assistance apps, or totally new kinds of interactive games. Once you understand this fundamental blueprint for sending actions across the internet, well, the possibilities are wide open.